Welcome. We are looking at the description of vectors, and there are several descriptions. One is to say that vectors are quantities with magnitude and direction. Other one is to say that vectors are quantities with one index when you refer them with respect to some coordinate frame of reference. And our problem now is to get rid of this dependence on frame of reference, because frame of reference is arbitrary. Anybody can choose some frame of reference, but the vectors have a life of their own. These are physical quantities like flux, for example, that does not depend on which frame of reference you choose to describe it. Okay. So, let us do this exercise. Let us say that I have a vector. Now, I have chosen a frame of reference to describe it. Let us say that this is x, y, z. Somebody else decides to choose another frame of reference, but it is not any arbitrary frame of reference. In most of this exercise that we are going to do, we are going to assume that the origin for the frame of reference remains the same, and you have another 3 mutually perpendicular directions. Right. Now, the relationship. So, how are this x prime, y prime and z prime related to x, y, z? That is given by what is known as the transformation matrix. What is a transformation matrix? So, you have all the old frame of reference here, x1, x2, x3, and you have the new frame of reference here, x1 prime, x2 prime, x3 prime. The A11 is, for example, the direction cosine between 1 and 1 prime. A12 is the direction cosine between 2 and 1 prime, and A13 is the direction cosine between 1 prime and 3. Similarly, A21, A22, A23, A31, A32, A33, right. These Aij's are direction cosines. For xi prime with xj, where prime is the new one and unprimed are old coordinates. So, when you do a coordinate transformation from x1, x2, x3 to x1 prime, x2 prime, x3 prime, or xyz to x prime, y prime, z prime, then we want to know what is the effect on the components that we are going to find out for this vector, which is the flux vector, let us say. So, J is my flux vector, which is being described by me by using x, y, z, by somebody else using x prime, y prime, z prime, except that the origin of these coordinates are the same. So, that I am assuming. Under that condition, if I want to know how the components x1, x2, x3 are related to x1 prime, y1 prime, z1 prime, that is basically given by the following expression. So, we say that x I prime is equal to A I j x j. Remember, we are using Einstein summation convention, which means that this will be summed over in terms of matrix notation. What we are saying is that x1 prime, x2 prime, x3 prime is equal to A11, A12, A13, A21, A22, A23, A31, A32, A33, multiplying x1, x2, x3. So, in other words, what we are saying is that if you think of this quantity x1, x2, x3, right, it could be j1, j2, j3, for example, that is the components of the j vector along x1, x2, x3. If that quantity, if you know, and if you know the direction cosines between the new coordinate directions and the old coordinate directions, and if you make a matrix and if you multiply that, if you get the components. If these happens to be the components of the same vector in the new frame of reference that you are dealing with, then you can define this quantity. So, this is then you can define this x as a vector. So, this is the third definition. What is the definition of a vector? We say that suppose if I have j and the components of j in a new frame of reference, if they are related to the old frame of reference through the matrix, which is the transformation matrix consisting of the direction cosines j I. J I are the components of the jth vector using the old frame of reference. J I prime are the components of the j vector using the new frame of reference. If suppose they are related through this, then we say that j is a vector. This is another way of defining vectors with respect to coordinate transformations. So, what is the idea here? We are thinking of vectors as quantities which have their own existence, and you can define them as quantities with direction and magnitude, but that is not generalizable. But if you refer the vectors to some specific frame of reference, then you can represent vectors in a column matrix fashion or by giving some components which can be represented using indices. So, you can define vectors as quantities with one index, for example. This is generalizable because then you will define a second rank tensor as quantity with two indices, a zeroth rank tensor is a quantity with no indices, and so on and so forth. So, it helps us to generalize, but it leads us to the problem that we have a quantity which has an existence of its own, but when we use this index based definition of the quantity, then we are necessarily defining it with respect to a frame of reference, and the frame of reference is arbitrary because the existence of the vector has got nothing to do with what frame of reference we decide to use to describe it. So, we want to see what is the effect of a change of frame of reference on the vector. Okay. So, then we define what is known as the transformation matrix, which is given by this A. A11 basically is the direction cosine between one prime direction, the new one direction, and the old one direction. Okay. A12 is the direction cosine between one prime direction and two directions. So, 1, 2, 3 are the old directions, and the 1 prime, 2 prime, 3 prime with respect to what is the direction cosines they make are defined as A11, A12, A13, A21, A23, etc. And this transformation then tells, if you take the components of a vector, if you do this transformation matrix left multiplication on that, you get the new components. So, any three numbers, for example, or suppose I take the j vector, the components of the j vector along x1, x2, x3 I can find out because I have the frame of reference. Somebody else uses some other frame of reference which has the same origin as mine, and the components that they have is given by x1 prime, x2 prime, x3 prime, and if I can find out the relationship between my frame of reference and their frame of reference in terms of the transformation matrix, and if I find that my components multiplied by the transformation matrix gives their components, then I know that this quantity is a vector. So, this is another definition of a vector. A vector is a quantity which transforms under a frame of reference change in a particular fashion. Namely, if I change the frame of reference from some x to some x prime, then the components change according to j I and j I prime related through a I j, where a I j is the transformation matrix which is consisting of the direction cosines between I prime direction and jth direction. So, that is how we form the transformation matrix, and this is the relationship. So, this is another way of defining the vectors, which is again generalizable. Okay. If we are going to show how this generalizes to higher order tensors. Okay. So, of course, scalars are quantities which are invariant. So, a scalar is invariant under coordinate transformation, right. I have the density of a material, it does not matter whether I refer to some frame of reference or some other frame of reference, okay. Or if I have temperature at some point, it does not matter what frame of reference I use, the temperature is a quantity which is independent of any frame of reference description, because it is a quantity which does not require any direction information, because it is just a number. So, it does not matter what frame of reference. But the moment you are describing a vector, if you use one frame of reference, you will get some components, if you use some other frame of reference, you will get some other components. Now, if these two components are related through a specific relationship, then that is a true vector. If that relationship does not exist, you can't take three numbers and put them in a column vector and say that this is a vector. It will become a vector only under a coordinate transformation if it transforms according to these relationships. For example, I can take the temperature at 3 points, right, 1, 2, 3, and then put them as a column vector and say that okay, this is a vector now. It cannot be, because if I do some other frame of reference with respect to which, then if I try to look at what happens to these numbers, if they remain the same, then that is really not a vector. But a true vector quantity will change its components according to the frame of reference you use in such a way that this relationship is always obeyed. So, that is how we define a vector, which is generalizable to higher order tensors, which is what we will do in the next lecture. Of course, it is also important to distinguish this transformation matrix from the second rank tensor that we defined. In form, this looks quite close to that D11, D12, D13 that we wrote. Okay, what is the difference between that and this? So, all these things we will take it up in the next lecture. Thank you.